When you ask a highly advanced artificial intelligence a complex question, there's this expectation of just flawless, machine-like precision.
Right, you expect perfection.
Exactly.
Hmm.
Like you ask it to solve a 10-step logic puzzle, and you just expect it to march through those steps perfectly. But reality is a bit messier.
Yeah, quite a bit messier, actually.
Because current generative AI models, I mean, they're incredibly fluent, they sound brilliantly confident, but they constantly mess up multi-step reasoning.
All the time.
A single arithmetic mistake in, say, step 3 of a 10-step derivation, and suddenly the entire chain of logic just falls apart.
It just cascades.
Right. And when you ask the AI to go back and fix its mistakes, it often ends up ruining the parts of the answer it actually got right the first time.
Which is incredibly frustrating for users.
It really is. So welcome to today's deep dive. We are unpacking a state-of-the-art foundational paper in generative AI today from Thomson Reuters Labs that tackles this exact problem.
Yeah, it's a fascinating read.
We are looking at why large language models are so incredibly bad at fixing their own work and how a new framework is completely changing the mechanics of AI reasoning.
The framework they introduce is called DISC, which stands for Denoising Iterative Self-Correction.
Denoising iterative self-correction. Got it.
Yeah, and it's a highly structured approach to what the field calls test time correction. By the end of this deep dive, you are going to fundamentally rethink what it means to ask an AI to grade its own homework.
I love that phrasing, grading its own homework.
Well, this paper completely shatters the default assumption in the tech industry that just giving an AI a second chance to look at a problem automatically leads to a better answer.
Okay, let's unpack this, because to understand why DISC is such a massive breakthrough, we need to look under the hood at how current AI correction physically fails.
Right, we have to look at the baseline.
The paper points out that standard self-correction methods, things that are widely used in enterprise software right now like chain of verification or self-refine, are actually highly flawed.
Very flawed.
These methods basically involve taking an AI's first draft, feeding it back into the model, and prompting it with something like, hey, review this and fix any errors.
Which sounds perfectly reasonable on paper.
It does, but the model just goes in swing. I mean, it is
It alters the text aggressively, yes.
And if you think about how these models actually function on a technical level, predicting the next token in a sequence, the recklessness makes sense.
The context window is everything.
Exactly. If an AI made a calculation error in step 4 of a logic chain, and you force it to rewrite step 4, you have just fundamentally altered the context window.
Right?
The logic in step 7 was mathematically dependent on the exact sequence of tokens the AI generated in steps 4, 5, and 6.
It relies on that specific history.
Yeah, so the moment the AI changes the text in step 4, its attention mechanism loses the thread. Step 7, which was previously perfectly fine, suddenly collapses like a house of cards because the foundation shifted.
That's a great way to visualize it.
Relying on standard AI self-correction is like hiring a mechanic who fixes your brakes, but accidentally cuts your fuel line while they're under the car.
Oh, wow.
You drive off the lot thinking you are safe, but you actually have a whole new, potentially worse problem.
What's fascinating here is that disruption of the original logic chain is exactly what the researchers called degradation.
Degradation.
Yeah. In the AI industry, the standard metric everyone loves to report to investors is just net accuracy.
Sure, the big flashy number.
Right. So if a new self-correction model gets a net accuracy boost of 2% on a benchmark, the company applauds, writes a press release, and ships it.
They just pop the champagne.
Exactly. But that headline metric completely hides the damage being done under the hood.
How so?
Well, if a self-correction method repairs 10 errors, but its altered context window introduces 8 brand new errors into answers that were originally completely correct, you have an inherently unreliable system.
Oh, wow. So the net improvement is technically 2, but I am definitely finding a new mechanic.
You'd have to.
I mean, I don't want a system that is just blindly guessing and hoping the math works out in its favor.
No one does,
Yeah.
especially not in high-stakes environments.
Right, like legal contract analysis or medical diagnostics. You just cannot tolerate a system that breaks true information to fix false information.
Which is why the authors of this paper discard net accuracy as the primary goal. They introduce a much stricter classification lens instead.
Okay, what do they use?
They measure correction quality using an improvement to degradation ratio, or ID for short.
ID ratio.
Yeah, think of this as the system's precision. For every one thing it breaks, how many things does it actually improve?
That makes total sense.
And they pair that ID ratio with the repair rate, which is basically your recall.
Meaning, Out of all the objectively fixable errors in the data set, what fraction did the system actually manage to isolate and fix?
Precisely. It's a much more honest way to evaluate these models.
So since those standard methods act like a reckless mechanic cutting the fuel line, the core engineering problem becomes, how do we build a cautious one? How do we build an AI system that knows when to keep its hands off the engine? Here's where it gets really interesting.
It's a brilliant approach.
The paper's central analogy for the DISC framework borrows its intuition from iterative denoising.
Right, which we usually see in image generation.
Yeah, we see this in image restoration and diffusion models. If you have ever seen an AI generator like Midjourney create an image, it doesn't just paint a picture from left to right.
No, it starts with static.
Pure noise. And over multiple passes, it mathematically subtracts the noise until the image gradually becomes sharp and recognizable.
Applying that visual concept to text generation is the core innovation here.
It's super clever.
It really is. DISC treats the AI's initial attempt to verify its own work as a noisy measurement.
So it expects the first pass to be flawed.
Exactly. It assumes the AI's first glance at its own logic is going to be blurry. It might hallucinate a problem where there isn't one, or completely miss a blatant error. Therefore, the verification process itself needs to be refined over multiple, careful passes to separate the true signal from the hallucinated noise.
So how does it mathematically denoise a paragraph of text? I mean, it breaks the monolithic AI down into a strict assembly line, right?
It does. The DISC pipeline divides the task into 4 distinct isolated roles.
Let's walk through those. First, you have the generator.
Right, which just produces the initial rough draft answer.
And second, you have the verifier. The verifier's job isn't to fix the answer, though.
No, not at all. It acts more like an investigator.
Yeah, it generates targeted questions, probing specific factual claims in the text, and then attempts to answer those questions to gather independent evidence.
Then third, you have the judge.
The judge.
The judge looks at the original answer side by side with the verifier's evidence and makes a ruling.
And finally, the corrector.
Right, which is the only component allowed to actually rewrite the text.
So the precision of this entire pipeline hinges on the judge, then.
Completely. This is what the researchers called the strict judgment gate.
The judgment gate.
Yes. The judge has a binary choice.
Hmm?
It evaluates the verifier's evidence against the generator's text.
Okay.
If the judge sees no explicit, undeniable contradiction between the two, it returns a systemic flag that says no mistake.
And the moment that flag is triggered, the entire loop terminates.
Exactly.
So the corrector never even gets to touch the text.
Not a single token. The answer is locked in and protected.
That is an incredibly defensive mechanism.
It is. The system is designed to aggressively protect the original text unless it has airtight proof of a failure.
Wait, let me push back on this architecture for a second.
Sure.
The paper mentions that this verified judge correct loop can run up to 3 times. They refer to it as a budget of k equals 3.
Yes, k equals 3.
If an AI model is hallucinating on pass 1, doesn't iterating the same prompt up to 3 times just compound the hallucinations? I mean, computing power is expensive.
It is very expensive.
Aren't we just burning a fortune in compute costs to have the AI hallucinate 3 times in a row and dig itself into a deeper, more confident hole?
Well, that is the exact vulnerability the judgment gate is built to prevent.
Really?
Because the gate requires explicit, logical proof of an error to proceed to the correction phase. It filters errors rather than compounding them.
Ah, okay.
The researchers proved this by testing the system on the GPQA Diamond benchmark.
Oh, right. For context for you listening, GPQA Diamond is a notoriously brutal dataset of graduate-level physics, chemistry, and biology questions.
Even experts struggle with it.
So it's the ultimate stress test for complex reasoning.
Precisely. And they found that on 79% of the examples in that dataset, the system exited early before ever exhausting that k equals 3 budget.
79%.
Yeah. The judge looked at the evidence, said, I see no undeniable contradiction, and stopped the loop on pass 1 or 2.
So you are not wasting compute on endless hallucinated spirals.
Exactly.
The paper actually includes an ablation study that highlights just how critical this gate is.
I love a good ablation study.
Me too. And just to clarify, an ablation study is basically the engineering equivalent of a neuroscience experiment, where you remove one piece of a system to see if the whole thing breaks down.
Perfect analogy.
The researchers literally removed the judgment gate from the code, forcing the corrector to rewrite the text every single time, just like a standard self-correction model would.
And the results of that ablation study were catastrophic for the AI's accuracy.
Catastrophic.
Yeah. When they removed the gate, The improvement to degradation ratio dropped by 2 to 4 times across the board,
2 to 4 times.
depending on which base model they used. Forcing the AI to correct without the judge's permission caused the degradation, the sheer number of correct answers that were destroyed by the AI, to double or even triple.
The gate is literally the only thing keeping the AI from destroying its own good work.
Without it, the model just eats itself.
There's a specific example in the paper using the Hotpot QA benchmark that beautifully illustrates how the gate preserves the good while trimming the bad.
Oh, the Australia example.
Yeah. The prompt asked the AI a seemingly simple question. Which New South Wales town is larger? Port Macquarie or Bonny Hills?
A classic retrieval question.
Right. The baseline AI they tested, which was Claude Sonnet 4.5, actually got the reasoning right. It correctly identified Port Macquarie.
But there was a catch.
Always a catch. In
Yeah.
classic LLM fashion, it buried the answer in this massive verbose sentence comparing historical population stats and geographical data.
And because the standard evaluation metric for the Hotpot QA benchmark requires an exact string match,
Right.
it just wants the specific name of the town and nothing else, the baseline AI scored a 0.
Wow. Despite doing the reasoning perfectly, it technically failed the test.
Exactly.
Right. But when they ran that exact same verbose output through the DISC pipeline, the verifier recognized that the formatting violated the prompt's constraints.
Yes.
The judge flagged the contradiction in formatting, and the corrector stepped in. It successfully trimmed the massive paragraph down to the 2 words Port Macquarie without altering the correct reasoning.
It kept the core logic intact.
Yeah. In a standard model, forcing it to rewrite might cause it to second-guess the town entirely and hallucinate Bonny Hills.
Because the attention shifts.
Exactly.
Mm-hmm.
DISC fixed the formatting without scrambling the underlying knowledge retrieval.
Which brings us to the next layer of this research.
Okay.
The architecture of a generator, verifier, judge, and corrector works. But a theoretical framework is only as good as the neural networks playing those roles.
That makes sense.
So the researchers asked a critical question. What happens when you use the exact same AI model to play all 4 parts of the pipeline?
Oh, I was thinking about the psychology of this. It is basically the equivalent of asking a student to grade their own exam.
It really is.
If I'm personally convinced that the capital of Australia is Sydney, and you ask me to grade my own geography test, I'm going to mark my answer as correct.
Of course you are.
My brain used a specific set of logic to arrive at Sydney, and when I review my work, my brain uses that exact same flawed logic to verify it. I'm going to suffer from massive self-confirmation bias.
If we connect this to the bigger picture, the researchers actually quantify your student analogy using a cross-model experiment on that same graduate-level GPQA Diamond benchmark.
Okay, what did they do?
They took a highly capable model, GPT-5.2, and had it play all 4 roles. It generated the answers, and then it tried to verify its own work.
And how did it do?
Out of all the complex errors it made across the dataset, it only managed to catch 18 of them.
18. So, left to its own devices, a state-of-the-art model is functionally blind to its own logical missteps.
Yes, because the neural pathways that led to the wrong conclusion are the exact same pathways evaluating that conclusion.
The weights and biases are identical.
Exactly. So they changed the
And
asparagus.
so they tweak.
They brought in a much weaker, smaller model GPT 4.1 Nano and had the Nano model generate the initial rough draft answers.
Okay, the weak student.
Right. Then they brought the powerful GPT 5.2 back. But this time, it acted strictly as an external verifier and judge for the weak model's work.
It's grading someone else's paper now.
Exactly. And suddenly, that exact same GPT 5.2 model found 51 errors.
Wait, really? It went from catching 18 errors to catching 51 just by separating the generation weights from the verification weights.
Yeah, that is a wild leap in performance.
That is insane.
It achieved what the authors call a massive super additive synergy.
Super additive synergy.
Yes. When they paired the weak generator with the strong external verifier and judge, they saw a net improvement of plus 34 on the benchmark.
Wow.
That is an order of magnitude better than what either of those models could achieve on their own.
So the takeaway for anyone building AI systems is profound errors and verification evidence share systematic biases.
They share the exact same blind spots.
Right. If you want true error correction, you must separate the generation role from the verification role.
You absolutely have to.
Okay, following that logic to its natural conclusion, the ultimate cheat code for reliable AI is just outsourcing the oversight.
Seems like it, right?
Yeah, have a cheap, fast, weak AI do the rough draft and pay for a massive, strong AI to act as the supervisor to clean it up. Problem solved, right?
You would think so.
Yeah.
But this is where the paper uncovers its most surprising and, frankly, its most concerning finding.
Uh-oh.
The researchers set up the ultimate stress test to find the absolute breaking point of this multi-agent pipeline.
Okay, what was the setup?
They created a hybrid configuration, a weak generator, the nano model, doing the drafting, a strong verifier, GPT-5.2, gathering the evidence.
Right.
But then they assigned the crucial role of the judge back to the weak nano model.
Wait, so you have a brilliant detective in GPT 5.2 gathering pristine evidence, but the detective has to hand that evidence over to an incompetent judge who makes the final call on whether to trigger the correction.
Exactly. And the results were staggering.
What happened?
Out of 197 examples in this stress test, the weak nano judge returned a verdict of no mistake 100% of the time.
100%.
It never triggered a single correction. Even when it was staring at 90 definitively, objectively wrong answers in graduate-level science, it froze.
It did absolutely nothing.
Nothing at all.
But if the strong verifier is providing the notes must be good, so the bottleneck has to be the judge's processing power.
Right.
Did the weak judge just fail to understand the complex physics evidence the strong verifier handed it?
Well, the researchers audited the logs to find out. The verifier's notes were virtually perfect.
Wow.
Yeah, in 89 out of those 90 wrong cases, the strong verifier produced evidence that explicitly, directly, and logically contradicted the wrong answer.
So the evidence was right there.
It was served on a silver platter. The bottleneck was entirely the weak judge hitting what the authors call a capability floor.
A capability floor.
Yes. Even with perfect evidence right in front of its digital face, the weak models simply lacked the cognitive capacity, the sheer parameter count, to process the contradiction and issue a command.
That's fascinating.
The paper identifies two fascinating, almost psychological failure modes for this. The first they call blindness.
Blindness.
This happened in 48 of the cases.
How does an AI go blind to text in its own context window? I mean, it's reading it.
Blindness occurs when the weak judge reads the contradicting evidence, but its limited neural network completely fails to map the semantic meaning of the contradiction.
So it reads it, but doesn't get it.
Worse, it treats the text as confirmatory, regardless of the actual content.
No way.
Yes, it reads a paragraph explaining why the math is wrong, and essentially outputs, yes, this evidence confirms my math is right.
It's a cognitive dissonance in code.
Exactly.
The AI is so biased toward its own initial generation that it bends the incoming evidence to fit its reality.
That's a great way to put it.
What was the second failure mode?
The second mode occurred in 41 cases, and they call it inability to act.
Inability to act.
This is the AI's equivalent of total paralysis.
Paralysis.
Yeah. In these cases, the judge actually successfully reads the evidence. It recognizes the contradiction. In its internal processing tokens, it explicitly states that the evidence disproves the answer.
But then what?
But then it just gives up. It concludes no mistake anyway.
I actually pulled the exact quote from the paper for this inability to act failure mode because the logic is hilarious in a slightly terrifying way.
Oh, read it. It's so good.
The weak judge is evaluating a complex chemistry question. The strong verifier hands it undeniable evidence proving the current answer is wrong.
Right.
And the weak judge literally writes out in its reasoning trace, quote, which contradicts the thermodynamic aspects supporting option D.
It sees it.
It openly admits, in plain English, that the evidence destroys option D.
Yeah.
But then in the very next breath, it generates the phrase, quote, therefore, the answer does not need correction.
It's mind-blowing.
It sees the fire, it points clearly at the fire, it explains the exact chemical makeup of the fire, and then decides everything is fine and the house isn't burning.
It is an incredible peek inside the black box of LLM reasoning. It proves that possessing accurate evidence is not enough.
No, clearly not.
The model, acting as the judge, must possess a minimum capability threshold to translate the recognition of an error into actual corrective action.
Right.
It requires a level of logical abstraction to say, because A contradicts B, I must initiate sequence C.
That makes total sense.
And if the model sits below that capability floor, The instruction following breaks down, and the entire self-correction pipeline is utterly useless.
So what does this all mean for you?
It's a big question.
Whether you are a developer building the next big enterprise app or just someone using AI to summarize financial reports or draft emails, the big takeaway is that AI is not a monolith.
Definitely not.
You cannot just ask a single AI to check its work and blindly trust the output. The architecture of these models means they will always suffer from self-confirmation bias.
They're wired to agree with themselves.
They will grade their own exam and give themselves an A, or worse, they will try to fix a typo and accidentally delete your entire logical argument.
Just slice the fuel line.
Exactly. If you want true reliability, you need strong external verification, and you need strict judgment gates to ensure that AI isn't recklessly fixing what isn't broken.
And this brings up a massive question for the future of the field, which the authors touch on in the limitation section of the paper.
Oh, right.
DISC works brilliantly in this specific study because it was tested on verifiable ground truths, mathematics, graduate-level chemistry, physics, logic puzzles.
Sure, hard science.
These are domains where an answer is either objectively right or objectively wrong. A thermodynamic equation balances or it doesn't.
Exactly.
But the tech industry is rapidly pushing AI into subjective, open-ended tasks.
Right, things like creative writing, deep trend analysis, or even navigating complex moral reasoning in autonomous systems.
They're already gray areas.
If a weak AI judge can suffer from an inability to act and freeze up when faced with objective, undeniable thermodynamic facts, how paralyzed is that same architecture going to be when the evidence itself is entirely subjective?
It's a scary thought.
We figured out how to build a cautious mechanic for a broken engine using DISC. But what happens when you bring that cautious mechanic a piece of modern art instead of a car and ask them to fix it?
I love that.
If we are moving toward a world where AI systems are constantly judging and correcting their own outputs in real time, the industry is going to have to figure out how to write the rules for a judgment gate when the truth itself is open to interpretation.
And until they solve that capability floor for subjective reasoning, relying on AI self-correction for nuanced tasks remains a massive gamble.
It is a fascinating frontier to watch. Thank you for joining us for this deep dive into the architecture of AI reasoning. Keep questioning the outputs, keep exploring the deep end of AI research, and we will see you next time.